Last time we talked about the constancy of the speed of light. At the very end of that episode, I left you with a question. Do you feel like digging deeper? Do you want to understand where this speed of light doesn't change really comes from? I also gave you a heads up. If we really get into it, this topic can be pretty brain-melting. A lot of you left comments saying, "All right then, let's argue it. Let's push back." So in this episode, let's talk about what happened before relativity ever appeared, where the constancy of the speed of light actually comes from, and what strange, almost uncanny things follow from that constancy. At the beginning of creation, there was light. In the book of Genesis, the ancients wrote that God created light on the very first day. That idea wasn't an accident. Without light, we would never know that beyond our immediate surroundings, there is still a vast universe. In the great religious texts of the West, the most important line is, "Let there be light." But now, that line has a kind of importance that's different from the past. Before, it was a thought in the mind of God. Now, we know it as an inevitability of natural law. By that same law, we get the sky above and the ground below. In that sense, it's not just that humanity is a prisoner of light, our universe is too. The earth and matter arrived in this world following in light's footsteps. And through one intellectual shift after another, step by step, we developed what we now call modern science. In the eyes of Plato, our observation of the world, what we can and cannot perceive, imprisons our thinking and limits how we describe the structure of the universe. But in the 2,000 years after Plato, hardly anyone paid attention to that warning. Later, when scientists finally began to take the nature of the universe seriously, one question tormented them for 400 years. What, exactly, is light? Among those modern scientists, the earliest to study the question seriously was Newton. To Newton, light was made of particles, tiny little bits. He called them corpuscles. But another group of scientists in his own era insisted, unanimously, that light was a wave. Newton was famously proud. He was convinced his peers and competitors were wrong, and he was right. To prove it, he designed a clever experiment. Supporters of the wave theory argued like this: white light is a smooth, pure light wave. When it passes through a prism, the glass corrodes it, so the beam gets scattered into different colors. By that logic, the thicker the glass, the more severe the scattering. Newton said, no, reality isn't like that. In his view, light is made of particles already carrying different colors. When those particles mix, we perceive white light. So, to show that the glass corrosion explanation was wrong, Newton did the following. He shone white light into two prisms facing opposite directions. After the first prism, the white beam spread into a colorful spectrum. Then, after the second prism, the dispersed spectrum recombined into a single white beam again. If the glass corrosion idea were correct, this should never happen. The second prism would only scatter the light even more. It couldn't possibly restore it to its initial state. Newton's experiment did reveal something important. White light is a mixture of different colors. On that point, Newton was right. But none of that proved that light is made of differently colored particles. In fact, what makes up white light is light waves of different wavelengths. Still, the wave theory ran into a huge problem. Light is a wave. But a wave of what? Every wave people knew back then required a medium to travel through. So what medium carries light? It was baffling. Wave theory supporters had no choice but to declare that all of space is filled with an invisible substance. They called it the ether. Sometimes, the answer to one physics problem shows up somewhere you'd never expect in some completely different corner of the physical world. This puzzle was no exception. Its answer was hiding in a world full of spinning wheels and crackling sparks. In that corner of the world stood a respected scientist, Faraday. He devoted himself to a hot topic of his time: the relationship between electricity and magnetism. Electric charges can attract and repel, just like magnets. But magnets always come with north and south poles. No isolated magnetic pole had ever been seen. For electric charge, though, there are individual positive charges and individual negative charges. Scientists and natural philosophers obsessed over the hidden relationship between charge and magnetism. A man named Hans Christian Ørsted accidentally found the first major clue. In 1820, during a lecture, Ørsted connected a battery through a wire. The current in the wire made a nearby compass needle deflect. Over the following months, he pushed further. He discovered that moving charge, what we now call an electric current, can make a wire produce magnetism, and that this magnetic influence makes a compass needle deflect tangentially around the wire in circles. It was a jaw-dropping experiment, and news spread quickly across Europe, then across the English Channel. If moving charge can create magnetism, then is there another connection? Can magnetism act back on charge? In 1831, Faraday recorded a crucial discovery in his experimental notes. He energized a coil wrapped around an iron rod, magnetizing that rod. In that instant, he found that current appeared in another coil wrapped around the same rod. Simply putting a wire next to a magnet didn't generate a current, but during the process of a magnet appearing or disappearing during change, current was produced. Then Faraday moved a magnet around a wire. The effect appeared again. As the magnet approached the wire or pulled away, current flowed. Just as motion of charge produces magnetism, motion of magnetism, or a change in magnetic field strength, can produce electricity. Hidden inside electromagnetic induction is something extremely deep. If you can't see it right away, don't blame yourself. The path to uncovering it is subtle. It took one of the greatest theoretical physicists of the 19th century to complete it. We'll get to him in a moment. But even at this stage, Faraday had already invented one of the most important concepts in physics, one that solved a problem Newton wrestled with for an entire lifetime and never resolved. It also became part of the foundation of all modern physics. The concept of the field. Faraday asked himself, how does a charge know that far away another charge has appeared so that it can exert a force? Newton had asked a parallel question about gravity. How does Earth know that the sun exists so that the two exert gravitational attraction? How does gravity get transmitted from one object to another? Newton never answered that. In Faraday's imagination, every charge is surrounded by an electric field. To him, an electric field was like a bundle of lines radiating outward from the charge. Add more charge, and you get more field lines. Place a test charge nearby, and the test charge feels the electric field at its location. The force is proportional to the density of field lines there. Faraday didn't use mathematical equations. He described the essence of forces through images in his mind. Similarly, magnetic fields can help us understand all kinds of magnetic force laws. With the concepts of electric fields and magnetic fields, we can restate Faraday's electromagnetic induction. When the number of magnetic field lines passing through a coil increases or decreases, a current is induced in that coil. Faraday soon realized this could turn mechanical energy into electrical energy. Put coils on the blades of a water wheel, place that wheel in a strong magnetic field, and as the wheel rotates, the magnetic flux through the coils keeps changing, so you get a continuous current. The year Faraday discovered electromagnetic induction, another great scientist was born. That scientist was James Clerk Maxwell. Faraday was 40 years older than Maxwell, and he inspired Maxwell's work. When Maxwell was young, he began focusing on electricity and magnetism, and after meeting Faraday, he took this blossoming field as his main mission. Using his mathematical talent, Maxwell re-expressed and re-understood Faraday's discoveries. He gave rigorous mathematics to what lay behind Faraday's lines of force, and pushed deeper into electromagnetic induction. To complete a unified theory of electricity and magnetism, Maxwell used Faraday's work to reveal their symmetry. Put simply, in Ørsted's experiment, moving charge produces a magnetic field. In Faraday's experiment, a changing magnetic field produces an electric field. In 1861, Maxwell first expressed these results as mathematical formulas, but he quickly found something missing. Electric and magnetic fields still didn't look symmetrical enough. Charge has to move to produce magnetism, but magnetism doesn't have to move. A mere change in magnetic field strength can produce an electric field. Maxwell realized that if the equations of electricity and magnetism were to be complete and self-consistent, he needed to add an extra term. He called it the displacement current. We don't need to worry about the equation itself here. What matters is Maxwell's inference. Yes, moving charge, electric current, produces a magnetic field. But motion is only one way to change an electric field. Maybe you don't need charges to physically flow. Maybe a changing electric field strength alone can also produce a magnetic field. So Maxwell imagined two parallel metal plates connected to a battery. Under the battery's action, the two plates carry opposite charges. Between them, an electric field forms. If you connect those plates by a wire, you get a magnetic field around the wire. With displacement current added, Maxwell's theory became mathematically self-consistent. Displacement current is like a fictitious current flowing between the plates. The real changing electric field between the plates corresponds to this displacement current. And the magnetic field between the plates is then the magnetic field produced by that displacement current. So the relationship between electricity and magnetism becomes: a changing electric field produces a magnetic field. A changing magnetic field produces an electric field. Without meaning to, what began as a field, inside equations, turned into a real physical thing, not merely a convenient way to describe interactions between charges. Electricity and magnetism became inseparable. From Maxwell onward, people no longer treated electric force and magnetic force as two different forces, because they are the same force in two different appearances. But Maxwell's genius didn't stop there. Don't forget the thing we started with: light. Light is one of the most basic physical existences, so common that we barely notice it. And yet, from Plato to Newton, even the greatest natural philosophers still found light mysterious. Maxwell used mathematics to show us what light truly is. Try this thought experiment. If you shake a small charged object up and down, what happens? A charge has an electric field around it. When you move it, the distribution of its electric field changes. According to Maxwell's theory, a changing electric field generates a magnetic field. When the charge reverses direction, the direction of the magnetic field flips too. Keep shaking the charge up and down. The electric field keeps changing, so it keeps inducing a magnetic field. The magnetic field keeps changing, so it keeps inducing an electric field. Back and forth, again and again, the shaken charge continuously produces new electric and magnetic fields, and these disturbances propagate outward. This is an electromagnetic disturbance. And when that disturbance forms a wave, it is an electromagnetic wave. Maxwell did something even more astonishing. He calculated the propagation speed of electromagnetic waves. His reasoning went like this: we can measure the electric field strength produced by two known charges. The field strength is proportional to the product of the two charges, so we define the proportionality constant as A. Similarly, we can measure the magnetic field strength produced by two electromagnets. Their magnetic field depends on the applied current. The field strength between the magnets is proportional to the product of those currents, so we define the proportionality constant as B. Maxwell pointed out that the propagation speed of electromagnetic disturbances produced by oscillating charges is completely determined by electric and magnetic field strengths. There is a definite formula. If experiments tell us A and B, then we can compute the wave speed. When Maxwell substituted the experimental data, he obtained a speed, about 300,000 kilometers per second, essentially the speed of light. And here's the key point. This speed wasn't obtained by measuring a distance and a time and dividing. It was obtained from electric and magnetic measurements. To ordinary people, that number might not feel like anything, but in a lightning flash moment, Maxwell knew. That number is the speed of light. In 1862, Maxwell recorded his reaction when he first derived this result. He essentially said that we can hardly avoid the conclusion: light is the transverse waves of the same medium responsible for electric and magnetic phenomena. In plain language, light is an electromagnetic wave. The question, why is there light, had haunted humanity for 2,000 years. And with that single sentence in Maxwell's work, the problem finally settled. Before Maxwell, people sought wisdom from God and creation stories. Even a genius like Newton still leaned on religion to think about the origin of light. But in 1862, everything changed. And then, in another eerie coincidence, in 1879, Maxwell died. That same year, Albert Einstein was born. Without Maxwell's discoveries, Einstein could not have become Einstein. Maxwell and Faraday built optics and electromagnetism for humanity. The new generation of scientists, growing up, had no choice but to wrestle with them. Einstein was among the earliest of that generation. As early as his youth, Einstein sharply noticed something. Maxwell's electromagnetic theory is elegant, but it hides a major problem. The problem is that Maxwell's equations are incompatible with Galileo's principle of relativity. This principle is simple, so let's say it plainly. Galileo argued that no person and no experiment can distinguish rest from uniform motion. For all observers who are at rest or moving at constant velocity, the laws of physics remain the same. Look up at the sky and it's easy to see. Relative to us, an airplane is moving. But whether you're on the ground or on the airplane, no matter what experiments you do, you cannot tell whether the ground is at rest and the airplane is moving, or the airplane is at rest and the ground is moving. Einstein's scientific life began on that high plateau of insight, and he quickly realized there's a terrifying chasm there. Between Galileo and Maxwell lies a contradiction that cannot be patched up, because under Galileo's idea, as long as I'm driving steadily at a constant speed, no sudden acceleration, the physics inside my car is the same as the physics in a laboratory. If my daughter in the back seat tosses up a toy, she'll catch it just fine. The everyday intuition she built at home works just as well inside the moving car. And if she throws that toy toward me, the toy follows Newton's laws, making a nice parabolic arc through the air and smacking me in the back of the head. Let's say the toy's speed relative to the car is 24 kilometers per hour, and my car is moving at 16 kilometers per hour. Then to a pedestrian outside, the toy's speed is the sum, 40 kilometers per hour. Everything still makes sense. But now imagine my daughter doesn't throw a toy. She switches on a flashlight and emits a beam of light. What does the pedestrian see? Common sense says, in the pedestrian's eyes, the speed of that light should equal the car's speed plus the light's own speed. But Maxwell's electromagnetism tells a different story. If you know the electric and magnetic field strengths produced by oscillating charges, you can calculate the propagation speed of electromagnetic waves. If my daughter measures the speed of light on the car as c, while the observer on the ground measures it as c plus 16 kilometers per hour, then the two observers must be measuring different electromagnetic field strengths, and that directly violates Galileo's principle of relativity. If two observers measure different field strengths, then we can tell who is moving and who is at rest, so uniform motion would become detectable. So, it seems Galileo and Maxwell cannot both be right. Many physicists lean toward Maxwell and tried to save the problem like this. They claimed the universe has an absolutely stationary reference frame. Maxwell's theory really applies only in that frame. Any observer moving relative to that frame will measure a different speed of light. And besides, if electromagnetic waves are some kind of electromagnetic disturbance, what medium is being disturbed? For centuries, philosophers had imagined a substance called the ether, colorless, transparent, filling all space. Just as sound waves propagate through air or water, people naturally assumed electromagnetic waves propagate through ether. Electromagnetic waves travel in the ether at a fixed speed, the speed Maxwell calculated. Then observers moving relative to the ether measure higher or lower light speeds, depending on their motion. Einstein's genius wasn't mainly in mathematics. It was in creativity. It was in the confidence to rethink assumptions. And it was the stubborn persistence that comes with that confidence. His enormous challenge was this: how do you reconcile two ideas that contradict each other? Choosing one and discarding the other is easy. Keeping both and removing the contradiction between them takes great creativity. So Einstein pushed toward an idea that sounds almost crazy. What if Maxwell and Galileo are both right? If they are both right, then in the car example, the car observer and the ground observer must measure the same electromagnetic signal strength and therefore calculate the same speed of light. In other words, no matter how fast you move, the speed of light is unchanged for you. This becomes one of Einstein's core postulates of special relativity. The speed of light in vacuum is the same for all inertial observers, independent of the motion of the source. Einstein then asked himself a brutally practical question: how do we measure the speed of light? The most common method to measure any speed is measure the distance traveled in a given time, then divide distance by time. So Einstein reasoned like this: if two observers each within their own reference frame. Take the same time interval, say, 1 second in their own frame, and measure how far light travels relative to them during that interval. Then they will measure the same speed of light. But then a further implication follows. If two observers always measure the same speed of light, then their measurements of distance or time must differ. So Einstein boldly asserted that these strange things are real. Maxwell and Galileo are both correct. All observers, no matter their relative speed, find that light moves at the same speed c relative to themselves. What differs is their understanding and measurement of time and distance. In everyday life, we often feel that what I see is what you see. My reality is your reality. Sadly, that's an illusion, and the reason is that light travels too fast. Sometimes we say, something happened right now. For example, a car crash in the street. But to be precise, it didn't happen right now, in our perception. It happened a little earlier, because the light from the crash scene needs time to reach our eyes. Once Einstein took that seriously, he asked, if observer A sees two distant events as simultaneous, then what does observer B moving relative to A see? To answer, Einstein gave an example involving a train. Imagine this scene. Observer A stands at the middle of a train car. He is stationary. Observer B is also at the middle, but he is moving forward inside the train, walking in the same direction. The train is traveling. At a certain instant, A and B pass each other. At that very instant, lightning strikes the front and the back of the train simultaneously. Smoke rises from both spots on the ground. For A, the light from the front and back smoke reaches his eyes at the same time. But for B, it's different. Because B is walking toward the front, he meets the light from the front sooner. At that moment, the light from the back has not yet reached him. A little later, he also receives the light from the back. Since B is in the middle, and since light still travels at the same speed c relative to B, B concludes. The front smoked earlier than the back. So who is right, A or B? Einstein's answer is shocking. Both are right. Einstein pointed out that the way a quantity is measured effectively defines the quantity itself. Sure, we can imagine a true world independent of measurement, but scientifically, that assumption doesn't work. If A and B are at the same place and the same time measuring the same thing, they will agree. But if A and B are far apart, their results may differ. Every measurement B makes tells B, the front event happened before the back event. Every measurement A makes tells A, the two events happened simultaneously. Neither A nor B can be in two places at once. To measure the time of a distant event, they must observe it, and that observation depends on the light emitted from the event. So after measuring light signals, A and B arrive at different judgments of simultaneity. In that sense, both are right. So here and now belongs to a specific place and a specific time. You cannot force the now of one place onto another place. Now let's give an even more mind-bending example. Suppose there is a third observer C on another train, moving opposite to B as it passes the station. Because C's motion is opposite B's, C concludes the left event happened before the right event, exactly the reverse of what B concluded. So C and B disagree completely. What one person sees as first, the other sees as later. This seems like a very serious problem. In our understanding of the world, causes always come before effects. But if the time order of events can depend on the observer, what happens to causality? Einstein's reply is, this kind of time order reversal can happen only for events separated by a large distance. And for such distant separated events, the time light needs to travel between them is always longer than the time difference involved, meaning no signal traveling at or below the speed of light can get from one to the other in time to create cause and effect. Influence. If the speed of light is the ultimate speed limit, then within that interval, a signal from one event cannot reach the other. So the two events cannot affect each other and cannot stand in a causal relationship. But what if two events occur at the same location? Would different observers still disagree about which came first? To address this, Einstein imagined a train with an idealized clock on one side and a mirror on the opposite side. Pay attention here. These two sides are perpendicular to the train's direction of motion, the left and right sides of the car, not the front and back. The clock emits a beam of light that reflects off the mirror back to the clock. Each time the light completes one round trip, the clock's hand advances by one tick. Assume one round trip takes 1/1, of a second. To someone on the train, the light goes straight across and straight back. Now ask, what does an observer on the platform see? The train is moving, so the clock and mirror are moving. The light beam's path is slanted, not straight. Obviously, compared with the train observer, the platform observer sees the light travel a longer distance, but the light speed is still the same, still c, so the round trip takes longer. So the 1/1, 0 on the train becomes 2/1, 0 for the platform observer. In other words, the platform observer concludes, time on the train runs slow. And here's what's even stranger. The effect is mutual. If there's an identical setup on the platform, then to the platform observer, the platform light travels straight back and forth. But to the train observer, the platform is moving, so the light path is slanted. So the train observer concludes that the platform clock runs slow. If you insist there is some absolutely objective observer, then you might say both are illusions. But don't forget what we said earlier. Measurement is reality. For A and B, the measured results are real. In their reference frames, those results are real. This is the logic behind time dilation, commonly derived with the light clock thought experiment. And the constancy of light speed produces another effect, arguably the strangest one of all. It changes the physical properties of objects as we perceive them. If I run toward you carrying a ruler at extremely high speed, the length you see is shorter than the length I see. In my eyes, it might be 10 centimeters. In your eyes, it might be only 6 centimeters. You might say, that must be an illusion. How could the same thing have two lengths? How could loosely arranged atoms compress together just for you? But let's go back to the old question again. What do we mean by real? If every time you measure my ruler, you find it is 6 centimeters long, then that ruler is 6 centimeters long. Length is not an abstract number floating in the void. We only know length through measurement. If measurement differs between observers, then length differs between observers. Now let's use an example to show how relativity closes the loop and remains self-consistent. Assume my car is 3.6 meters long. Your garage is only 2.4 meters deep. Clearly, my car cannot fit in your garage. But according to relativity, if I drive fast enough, you will measure my car as only 1.8 meters long, at least while it is moving, so the car can fit in your garage. But switch perspectives. To me, driving the car is 3.6 meters long. Your garage is rushing toward me at high speed. If I measure it, the garage is no longer 2.4 meters deep, it may be only 1.2 meters deep. Then my car fits even less. So which view is correct? Surely the car cannot both fit and not fit. But wait, are you sure that's obvious? Return to your perspective first. Suppose you installed doors at the front and back of the garage. To make the procedure safe, you do this. While my car enters the garage, you keep the back door closed and the front door open. Once my whole car is inside, you close the front door, and at the same time you quickly open the back door so my moving car can safely exit through the back. From your view, nothing is strange. My car is shorter than your garage, so of course it can be fully inside with the doors operated like that. Now return to my view. Remember, for distant events, the order of events I infer may differ from yours. Here's what I see. I see your small garage ahead. You open the front door so my car can enter. Next, right before I smash into the back door, you kindly open the back door. Later, after my car's rear has entered, I see you close the front door. So in my view, my car was never fully inside the garage while both doors were closed because your garage is too small. You and I see realities based on the measurements available in our respective frames. In my frame, the car is longer than the garage. In your frame, the car is shorter than the garage. That's just how it is. The key is this. At any given moment, we can only be in one place. We have a clear grasp of the reality at that place. But when we consider other corners of the world, we must rely on distant measurements, and those measurements can differ by observer. Put differently, in everyday situations, because both the garage and the car are tiny compared with the distance light covers in the relevant timescale. We treat the car fits versus the car doesn't fit as an absolute fact. But in the real universe, for us to actually observe the difference in these perspectives, the car and the garage would have to be extremely, extremely long. At such large distances, we can't treat "did the car fit" as a single, perfectly objective event, because in such a scenario, light needs time to travel from the car's front to its rear. So the front passes the back door, and the rear passes the front door are not the same event. They are two different events with an order. And different observers can disagree about that order. That's why this story feels so brain-burning. Einstein, in Relativity, revealed a completely new reality, a world built on Galileo's principle of relativity and Maxwell's electromagnetic unification, a world that wipes away the objectivity we instinctively assume, a world where reality depends on measurement. All these weird consequences come from believing the speed of light is constant. And we believe the speed of light is constant because light is an electromagnetic wave, and its speed arises from electromagnetic law rather than simple distance divided by time. So when you challenge the speed of light is invariant, you aren't merely challenging a single measurement result. What you are really challenging is this whole step-by-step chain of inference across the development of physics. Don't forget, light speed is constant, is almost a byproduct, a consequence of deeper principles. Meanwhile, those deeper theories have enormous power elsewhere and have been confirmed by countless experiments. To overturn them, you wouldn't only overturn light speed invariance, you'd have to overturn the entire structure of physics built on top of them. Finally, let's talk about how the scientific community explains these strange relativistic effects. This brings us to four-dimensional spacetime. In the Q&A of the previous section, I told you the story of prisoners in Plato's cave. They can't see the real objects behind them, only shadows projected onto a wall. If a ruler rotates behind their backs, they cannot see the rotation itself. They only see the shadow on the wall lengthen and shorten. But if we look from above, it's easy to understand. The shadow shortens because the ruler rotates at an angle relative to the wall. From that overhead view, the ruler's true length never changed. The invariance of light speed and the new relationship Einstein revealed between time and space reflect a deeper connection. Observers are living in a four-dimensional universe where time and space have equal status. Observers moving at different speeds see nothing more than different three-dimensional projections of the same four-dimensional reality. Return to the ruler in relativity. When we observe a fast-moving ruler while we are slow, we find its length is contracted. What we are observing is the projection into three-dimensional space of an object moving through four-dimensional spacetime. The greater its extent along the fourth dimension, the faster it moves through time, relative to us, the shorter its projection in three-dimensional space. But if an observer moves alongside the ruler at high speed, then for that observer, the ruler's length is unchanged. Length contraction and all other relativistic effects can be understood from the viewpoint of spacetime. In four-dimensional spacetime, there exists a spacetime length that is the same for all observers. The spacetime interval. Different observers, different three-dimensional pictures, are merely projections of that same invariant interval. So on the surface, Einstein's relativity seems to make the physical world more subjective, varying person by person. But in truth, relativity is not relative. It is a theory of something absolute. Your measurements of space and time may be observer-dependent, but the measurement of the space-time interval is universal. Who would have thought that Faraday's spinning wheels and magnets would ultimately rewrite our view of space-time? And yet, in hindsight, we can at least say this: electromagnetic unification had already revealed a new world to us. Let's return one last time to the age of Faraday and Maxwell. This chain of revolutions began with a charged particle moving in a magnetic field, experiencing a special force, what we now call the Lorentz force. Now stand in the particle's shoes and think about the same phenomenon. In the particle's reference frame, the magnet is moving while the particle is at rest. But ordinarily we say a stationary charged particle cannot experience magnetic force. It can only experience electric force. In other words, in the particle's frame, the force it experiences must be electric, not magnetic. So something that looks like magnetism in one observer's eyes appears as electricity in another observer's eyes. What connects the two is motion. Different observers in relative motion see different physical pictures. This is the core of electromagnetic unification. Motion, the topic. Galileo studied earliest 3 centuries later revealed an entirely new reality to us. In that world, not only are electricity and magnetism unified, time and space are unified as well. If you only read the opening chapter of this legend, no one would guess it would become so vast and so epic. And that's exactly where the charm of this story lies. Alright, that's it for this episode. See you next time.